Hi everyone, welcome back. In case of public key cryptography, having a key is only one part of the equation. Knowing that it's truly from the right person is very important. In this video, let's look into one of the most critical challenges in cryptography: how to securely distribute public keys and ensure that they haven't been tampered with or impersonated. If you are wondering, the name being public key, why are you bothered about securely transmitting it? Because sharing a public key securely is crucial to prevent man in the middle attacks, to ensure authenticity and maintain integrity of communications. To mitigate risks involved, public keys must be shared securely. So let's see what are the different ways of effectively and securely sharing public keys. In public key cryptography, the two keys used are mathematically related to each other, but knowing one key does not divulge the other key. We usually call them as public key and private key. The name itself is going to tell you that public key is made public, whereas the private key is kept secure. In cryptography, it is a very tedious task to distribute the public and private keys between the sender and receiver. Now, there are two aspects for key management. The first one is, how do you securely distribute public keys with authentication to ensure that it is the right person who is claiming to be the owner of the public key. The second aspect is, how can you use asymmetric key cryptography or public key cryptography to distribute secret keys that are used for symmetric encryption. So there are two aspects of key management here. Now, there are four techniques that are usually discussed which have been proposed for securely distributing the public keys. The first one is the public announcement. The second one is publicly available directory. The third one being public key authority. And the final one is public key certificates. Let us see each one of these things in detail. The first one is the first way of sharing the public key is through public announcement. Now, once again, it's a self-explanatory term. You announce the public keys to everyone. Here, the public key is broadcasted to everyone. Any participant can send his or her public key to any other participant or broadcast the key to the community at large using news groups, internet mailing lists, etc., etc. It is one of the most easiest ways of sharing it. I simply broadcast it. I can print it. I can give it to everyone. I can distribute it. I can post it on the internet form or social media, anything. I can do whatever I want. But the major weakness of this method is a forgery. Anyone can forge such a public announcement. That is, someone can claim to be me and then distribute his or her public key as my key. Some user could pretend to be user A and send public key to another participant or broadcast such a public key. By the time this comes to my knowledge and I announce that it is not my key, the damage has already been done. Until such time as user A discovers the forgery and alerts other participants, the forger is able to read all encrypted messages intended for A and can use the forged keys for authentication. So this is not the best way of sending or sharing the public keys because there is always a risk of forgery or impersonation. So we move on to the next one, which is called as publicly available directory. Once again, you have a publicly available directory which is maintained here, which holds all the public keys of the participants. It's kind of a telephone directory or a register kind of thing where each and every participant go and record their public keys into that. Maintenance and distribution of the public directory would have to be the responsibility of some trusted entity or organization. The authority maintains a directory with a name, public key entry for each participant. Let us say that if my name is Mukesh and there will be an entry called as Mukesh and my public key, PUM. Similarly for everyone. So whomever names, for Ram, you have another public key. Like that, this directory is maintained with a list of all the participants and their corresponding public keys. Each participant registers a public key with the directory authority. The registration would have to be in person or by some form of secure authenticated communication. That means if I have to register with the directory, I have to show my credentials. I have to ensure that it is me who is actually giving this public key to the directory, and only then this key will be placed inside the directory. A participant may replace the existing key with a new one at any point of time. That means if I want to change my public key or if I feel my public key has been compromised, I can go to the directory and change it at any point of time. Participants could also access the directory electronically. That means I can go access the directory at any point of time. It should be available all the time. But the problem here is if an opponent succeeds in obtaining or computing the private key of the directory authority. So this, if an attacker directly compromises or attacks the directory and is able to successfully compromise this, the opponent could authoritatively pass out counterfeit public keys. That means he can put his or own key here, public key of the attacker, and he can pass it off his public key as my public key through this directory, and subsequently impersonate any participant and use drop-on messages sent to any participant. Another way to achieve the same end is for the opponent to tamper with the records kept by the authority. Also, he might be, if he is successful uh, if he is successful in attacking the directory, he could also tamper the records that are maintained by the directory, which involves all the public keys of these participants. So there is a single point of failure in this kind of scenario. If we move on, the next thing is you maintain a public key authority, assumes the existence of a public authority that maintains a dynamic directory of public keys of all users. The public authority has its own private key, public key that it is using to communicate to users. That means, imagine in this, look at this diagram, which we have taken from the Starring's textbook. We have a public key authority here, which has a private and a public key pair associated with it. Public key of the authority being PU auth and the private key being PR authority. Let us assume that. Now, each and every one of these entities, A, B, who wish to communicate, do know the public key of the authority. So what happens here? You can see a series of steps and communications that are happening. Now, in the first one, if A wants to initiate a communication with B, what A will do is he will send a request to the public key authority for the public key of B and will also add a timestamp to this particular message. So request concatenated with the timestamp to the public key authority. Once the PKA or the public key authority receives this request message, it will send a response in the second one. This response is usually encrypted using the private key of the authority, which includes the public key of the responder, which is requested by A, which is nothing but the public key of B, and also a request and the timestamp which is sent by A. This is going to ensure A that this message is a response to the earlier one, which is sent in the first one. So A now knows that it is not an old reply, but it is a reply to the request it has sent. Now, because A knows the public key of the authority, it will be able to decrypt this message and obtain the public key of B, PUB. Okay. Now, after these two messages, what A will do is, now A is going to send a message directly to B, which is encrypted using the public key of B, which includes the ID of A, the identifier of A, and also something called as nonce in the third message, which we call as NONCE nonce. Nonce is typically a pseudo-random number or a bit string used only once in a cryptographic communication to prevent replay attacks and also ensure integrity of the message. So a nonce is used only once. It uniquely identifies this transaction. This message is sent to B. Now here, the third message can only be read by B because it is being encrypted by public key of B. It can only be decrypted by private key of P, isn't it? So upon receiving the message from A, then B also should find out the public key of A. These two messages, 4 and 5, repeat the same steps through which A received the public key of B from PKA. Now, after 4 and 5, B will also receive the public key of A. Now, if you understand, messages number 2 and number 5 are going to ensure both A and B that the public keys which they are receiving are genuine, because these keys are encrypted using the private key of the authority. Only the authority does have the knowledge of the private key, and nobody else can forge these messages. So messages 2 and 5 cannot be forged by somebody else, isn't it? So after 4 and 5, once B receives the public key of A, it is now going to send a message which includes the nonce N1 and another nonce N2 selected by B. This is selected by B. This is selected by B. Here, this message number 6 is going to ensure that A is indeed talking to B. If you ask me, sir, how does it work? Because unless until it's B, no one will be able to decrypt this message and see what is N1. Because it's B, he is able to decrypt this message using his private key, and only then he doesn't have the knowledge of N1. Similarly, A also has to be ensured, or B also has to be ensured that it is indeed talking to A. So what happens is, after receiving message number 6, A will send another message back, which is nothing but it will send nonce N2 back to B using the public key of B. So both 6 and 7 are identifying that both A and B are indeed communicating with one another. There is no intruder or an attacker who is masquerading as A and B, because only A and B do know their corresponding private keys, and only if they know their corresponding private keys, they will be able to decrypt the messages to find out what is N1 and what is N2. Understood? So this is public key authority, and of course it looks good on paper, it looks nice, it provides all the services that are intended, but it does have some drawbacks. For any communication between two users, the central authority must be consulted by both users to get the latest public keys. That means if A wants to communicate with B again after some time, it has to go through all these steps again. Similarly, if A wants to communicate with C, once again it has to go through all the steps, which makes the central authority should be available 24/7. If at all the central authority goes offline for whatever reason, all the communications get to a halt, will be halted. They cannot proceed communication because of no public authority, and it is unavailable to issue the keys. This clearly leads to an undesirable bottleneck. That means once again you're talking about single point of failure. If the public key authority is unavailable for whatever reason, or if it is attacked by an attacker, all the communications are going to be stopped. So what happens is, and once again, as we discussed in the second technique, the directory of names and public keys maintained by the authority is vulnerable to tampering. If an attacker can access it, if he is able to get into the records, he will be able, or he or she will be able to tamper it. So we need an even more efficient scheme of securely communicating public keys. So we have come to the next technique, or next way of handling public keys is through something called as certificates, which is the most efficient way of doing it, and currently the way which is being used for communicating the public keys between different entities across the internet also. These certificates can be used to exchange keys without contacting a public key authority in a way that it is as reliable as if the keys were obtained directly from a public key authority. So how does it work, sir? You are saying it is good, it is efficient, it is secure. But how do you do that? A certificate, what it does do is it binds an identity to public key with all contents signed by a trusted public key or certificate authority. Here we come across an entity called as CA. CA stands for Certificate Authority. CA stands for Certificate Authority. What do you do is, this is user A. What he will be doing is, he will be sending his details, his credentials, along with his public key to the certificate authority. This certificate authority, it might be a government agency or a financial institution which is trusted by the community. Upon checking his credentials, what it will do is, it will simply issue a certificate. This certificate will hold or will bind user A and his public key, which is signed by the CA. We'll discuss more. So A user, what happens now, sir? I got my certificate. What can I do with it? A user can present his or her public key to the authority in a secure manner and obtain a certificate. The user can then publish the certificate. Anyone needing this user's public key can obtain the certificate and verify that it is valid by the way of the attached trusted signature. That means once I have the certificate, any certificate is signed by a particular authority. If I am able to verify that the certificate is genuine, I can trust it and I can then share the public key with my peers. I can obtain the public key of my peer also. Now you can see here, this diagram, what it does is A is going to send his public key to the certificate authority and he will be issued a certificate called as CA. What it does is this certificate is encrypted using the private key of the authority. So nobody else can create the certificate. What it is contained, the timestamp at which it is issued, to whom it is being issued, and what is the public key of the entity. These are the three main components, isn't it? Now, simply both A and B will get their respective certificates and they can simply exchange the certificates for securely communicating the public keys. Because B can also verify this, B can decrypt the CA using the public key of the authority. It will be ensured that the certificate is issued by the CA, nobody else. Similarly, A can also be ensured that CB is issued by certificate authority and they can collect the public keys of A and B and then can start their communications. This certificate scheme does have some requirements. It has to satisfy these requirements. What they are is any participant can read a certificate to determine the name and public key of the certificate's owner. That means if A receives CB, he should be able to read the contents of CB, to whom does it belong, and what is the public key of B. Any participant can verify that the certificate originated from certificate authority and is not counterfeit. That means once A has received the CB, as I said, the first requirement should enable A to read its contents and get the public key. The second thing is A should be ensured that CB is actually issued by the certificate authority itself. But how can you do it? A can verify it by decrypting this. Once he is able to decrypt it, then it automatically is ensured that the CB is actually from the certificate authority itself, because no one else will be able to counterfeit using the private key of the authority. The third requirement is only the certificate authority can create and update certificates. That's obvious. Nobody else other than the certificate authority can create CA and CB or even update them also. Any participant can verify the currency of the certificate. Currency is nothing but the timestamp and the date till which this, or date or time till which this certificate is valid. So anybody can be able to verify and validate the currency of the certificate, whether it is genuine or not, till what time it is available, it is valid. All these are the requirements for this certificate scheme. And public key certificates are the most widely used for distribution of public keys in modern day world. One scheme which is a standard is something called as the X.509 standard. These X.509 certificates are used in most security applications, including IPsec, SSL, TLS, secure electronic transaction, and even in S-MIME. So I did make a video on X.509 standard, and you can observe what are the contents that are there in X.509, what are the additional features that have come in version 3 and so on. So please do check out that video to learn more about how a public key certificate looks like. Okay, till then, take care and good luck.